In this lecture, we are going to understand Dijkstra algorithm. Dijkstra algorithm basically operates on graphs where we find shortest distance to reach to each node. In this problem, we will be given a graph. Every edge will be having some weight. We need to find the shortest path for each vertex from the given source node. For instance, in this graph, A is the source node, so we need to find minimum distance to reach to every node from A. For that, we will be having a table or a matrix of shortest distance for every single vertex, and will update or improve them continuously. Initially, we give start node 0 as minimum distance, and to all other nodes, shortest distance will be infinity, as we don't know the distance to these nodes yet. So we start to explore node A. 4 edges are coming out of A, which are B, D, F, C. So we check for every vertex. If the distance from the current source to vertex is smaller as compared to the current upper bound, for example, to go from A to B, the current upper bound is 0 because at A we are having 0. So A to B distance is 3. And in the table, distance is infinity. So we check if 3 is smaller than infinity. If it is, we say that the best way to go to B is A. So we update the distance as smallest distance for B. Next edge is C. A to C distance is 5 and upper bound is 0, which is less than infinity, so we update the distance for C as well. Similarly for D, distance from A to D is 6, which is less than infinity, so we update it in the table. And then for F, it is 8, it's less than infinity, we update it in the table. So now we are done with A because we have traversed all the adjacent nodes. So the next we choose the unexplored vertex, which has minimum distance. So see the table, the vertex with minimum distance is B. So let's process B. Now B is having value 3, so the upper bound is 3. So if we visit any node after visiting B from A, can we improve the distance to get to these adjacent vertex from A? If we can, we will update the distance with the new value. So the neighboring vertices of B are A, D, E, G, right? A is already visited, or if you even try to go to A through B, then the path will be A, B, A, which will be 3 plus 3. The upper bound at B is 3, so it will be 6. So that we don't prefer anyways because it is having value 3 already and A is having value 0. Next is D. The current distance to get to D is 6 from A, right? You can see this on the table. And if we go through B, it will be 3 plus 4. That will be 7, which is not less than the current one. So going through this path is not a good choice. We need not to improve it. Now we're going to look at E. If we choose B to get to E, the distance will be 3 plus 2, which is less than infinity, so we will update 5. Next is G, which is less than infinity. Here we are having 5 distance and the upper bound is 3, so the distance becomes 8. So let's update it here. Now B is also visited. The minimum distance in this table is for C and E, right? So next we're gonna start with C. So here adjacent vertices are A and F. A is already visited, so we have only F. So for F, if we go through C, the distance is 4 plus 6. But F is already on 8 if we go directly from A. So we are not going to take that. Now C is also visited. Next we will process E. Here the adjacent vertices are B and G, and you know that B is already visited, so we have G. So for G, the upper bound here on E is 5 and the distance is 10, so it becomes 15, which is greater than 8. So we won't update it because we have a better path when we go through B. Now E is also visited. Next minimum is D, so we're gonna process D. So see, if you can improve the distance to reach to F, it will be 6 plus 1, which is 7, which is actually less than the current one. Current one is 8. So we update 7 as the minimum distance for F. Now we start processing F. So here the adjacent vertices are A, C, D, G, right? Where A and C are already visited, and for D, it is 8 plus 1, which is greater than 6, so we won't update. For G, it is 8 plus 8, 16. Again, it is greater than 8, so we won't change it. So basically, we are minimizing the path from the very start, and we repeat the process for the whole tree. We will get the best path to reach to destination, as every time we go to a vertex, we know we are on the best way to reach to this vertex. So if we apply this rule throughout the graph, we will generate the optimal solution. Now, before jumping into the code, let's talk a bit about how we're going to have this data. So see here, we will be having a matrix where the rows and columns of this matrix will represent the vertices. You can see A, B, C, D, E, F, G. These are the vertices, and the values in this matrix are the respective distances from one vertex to another vertex. As you can see here, in this table, the A to A distance is 0, the A to B distance is 3, the A to C distance is 5, the A to F distance is 8, the B to A distance is 3, and so on. So this matrix is having all the distances. So this is one array or one matrix that we will be having, and we will be having another array that will store the shortest distance that we are finding using this algorithm for each vertex. So the index of this array will represent the vertex. As you can see, we are having 0, 1, 2, 3, 4, 5, 6. These can be A, B, C, D, E, F, G, and the shortest distance will be the values in this array. And one more array to keep the track of already visited vertices. So it will store Boolean, true if the node is already visited, and false if it is not visited previously.